All right, so picking up where we left off, we actually finished on this last calculation, calculating the entropy change for a reversible reaction. And reversible here is in the thermodynamic sense, where it's sort of on the knife's edge of, in this case, freezing or melting, where essentially an infinitesimally small change in the temperature will cause it to go back and forth. And the whole goal of talking about entropy and everything so far has been to determine whether or not, or to predict whether or not reactions will be spontaneous, whether they'll occur without outside influence. And so towards that end, we've been defining this idea of entropy, which is, in a sense, it's chaos quantified. So the more that energy or the more microstates that a system can have, the more entropy there is. So by increasing that, you increase entropy, which you need to know because we talked about the second law of thermodynamics, where the entropy of the universe is always increasing. So getting into then, or continuing then from that idea, right? We know what entropy is. We can calculate entropy for things that are exactly at their boiling point or exactly at their freezing point, these reversible reactions or these reversible processes. But we need to do more than that. We'd like to be able to predict whole reactions. And we before talked about enthalpy, right? So whether a reaction is exothermic or endothermic, and if we could predict if a reaction is going to be spontaneous just using that. But there are spontaneous endothermic reactions. Now, a process like water, so like water freezing, if it's below 0 degrees Celsius, that'll be a spontaneous process. But if the surrounding temperature is greater than 0 degrees Celsius, then melting is the spontaneous process and not freezing. So there's obviously a temperature component to whether or not something is spontaneous. And that's because for any process, for any spontaneous process, the entropy of the universe increases. And so far, we've only really talked about the entropy of our system or our reaction itself. But that's not in a vacuum. It's not by itself. Any change in our reaction has to have an effect on its surroundings. So we can relate the entropy of our system to the entropy of the universe by including the entropy of the surroundings. So if we do something to our system that changes the entropy, how does that affect the surroundings? And then how do those two things together affect the entropy of the universe? So we can decrease entropy for a process. So for freezing, right, if you have water, liquid water freezing into solid, is that an increase in entropy or a decrease in entropy? If we're going, if we have water, here, I'll write it down. Is water freezing a decrease or increase in entropy? It's a decrease in entropy, yeah. So I guess put more space between my question and my rambling. So water freezing, you're taking these water molecules that are floating around, they're able to move places, right? Lots of microstates, possible microstates, and you're locking them into a crystal structure. So you're decreasing the entropy there. And so, while again, we're trying to figure out how do we determine if something's spontaneous, so we can have decreasing entropy. That can happen as long as decreasing the entropy of our system, or water, increases the entropy of the surroundings by more. So there's a net effect. And that net effect on the universe, the entropy of the universe, has to be positive. So we can sort of map this out. We can graph it. All right, so why does freezing water increase the entropy of the surroundings? Well, freezing is exothermic. So that delta H of fusion is the heat released per mole for water freezing. And that releases that energy, that heat, and it disperses it to the surroundings. And once that heat's in the surroundings, it can continue to spread out. And so our heat, or delta S of the surroundings, increases. This is a little bit hard to see because they're, oh, that did not want to be a straight line. So if I do this, outline this, and then it'll can I please do this? Thank you. All right, so that amount that the entropy of the system decreases is a smaller rectangle, a shorter rectangle, than the entropy of the surroundings has increased. So if you added those two things together, you'd get a net positive increase in entropy. So we're actually dispersing more energy by freezing than we are, well, not freezing. So releasing that energy to the surroundings. So freezing of water is not spontaneous at all temperatures, though, right? Greater than 0 degrees C, it's not spontaneous. And that's because the amount of entropy introduced by releasing heat depends on how hot it is already. So if the surroundings are already warm, releasing some amount of heat into those surroundings doesn't make a big difference. Actually, the example used in the book is, it's kind of like if you give a poor man $1,000, that's a huge difference for him. But if you give somebody who's already got $1 million, you give them $1,000, they're like, this is, a drop in the bucket. So similarly, if the surroundings are hot, they already have lots of heat energy. Giving off a little bit of heat energy doesn't increase that entropy very much. So that temperature dependence is based on how much entropy is already in the surroundings. So we can also represent that mathematically. Not on the next slide, but I think the slide after. So under a low temperature situation, I'll try and draw the box again. So low temperature situation, the surroundings are cold, right? Not a lot of heat energy. So when the water freezes and releases that heat to the surroundings, it's a net positive. That there's more entropy gained by the surroundings than is lost by the system. But in a hot environment, there's more energy that's actually, what would take more, your net entropy would be negative. So you'd be decreasing the entropy of the water more than you'd be increasing the entropy of the surroundings. So it's these two things together. And eventually, we want to get to a point where we don't have to rely on this calculation of the entropy of the surroundings, because we can quantify our system. We know what's in our system. The surroundings is kind of nebulous. So we can quantify that in terms of our system. Right? So if we're saying that it's this heat that's being released by our freezing. So if by freezing we're releasing heat, that heat goes into the surroundings and causes the entropy of the surroundings to change or increase. So we can say, okay, the heat released by the system, Q of the system, has to be related to this, proportional to the entropy of the surroundings. And since negative Q is heat being lost by the system, right? Negative Q is proportional to delta S. So for exothermic processes, we're going to increase the entropy of the surroundings. And for endothermic processes, where Q is positive, it'll decrease the entropy of the surroundings. Now, temperature is also a factor here. Right? We know that as things get hotter, that amount of heat released by the system matters less and less. So the change in enthalpy, or the change in entropy of the surroundings, is inversely proportional to the temperature. So as it gets hotter, we're dividing that negative Q system by a larger T. And so the change in surroundings, entropy of the surroundings is less. And then when we have constant pressure and constant temperature, we can use a change in enthalpy. So for a chemical reaction, we have standard enthalpies. We'll talk more about those later. But we can plug in those standard enthalpies now and say, hey, for this system, we can quantify this amount of heat lost per mole of reaction or reactant, and calculate now the change in the entropy of the system entirely based on, entropy of the surroundings entirely based on our system. So we're removing variables that are hard to quantify, putting everything in terms that are easier to quantify. Okay, put some of this into practice then. So we can calculate the entropy change in the surroundings associated with the reaction, and we're given a temperature here, occurring at 25 degrees C. So we'll use this new equation that we came up with. The change of entropy of the surroundings is equal to the negative change in enthalpy of the system divided by temperature. Remember, temperature here has to be in Kelvin because the units of entropy are, joules per Kelvin. So we'll have delta S, the surroundings, equals the heat delta H of the reaction. And because we want to calculate this to get entropy, we need to convert this kilojoules into joules. So it's going to be 163,200 joules divided by, and if you've forgotten, 273.15 plus 25 degrees C will give us Kelvin. So that'll be 298.15 Kelvin. Okay, so 163,200 divided by 298.15 means that our change in entropy of the surroundings is 5.47 times 10 to the 2 joules per Kelvin. Oh wait, I forgot the negative. Negative delta H. So that means that when we plug in delta H, to put that negative on there. Because this is a, well, let me ask a question. Is this an exothermic or endothermic reaction? Endothermic. So positive delta H is an endothermic reaction. So it's absorbing heat from the surroundings. So our change in entropy for the surroundings should be negative. At least in terms of, the temperature change, or the heat change. So then to determine the sign of the entropy change for the system, now we're looking a little more general because we haven't talked about a way to quantify really for the system how to calculate that entropy change. But is the entropy of this reaction increasing or decreasing? So for this, right, there's a couple things that we talked about so far that change the entropy. One of those would be changing states. Here we're going from gases to gases. The other one is the number of moles of gas. So in our reactants, we have 3 moles of gas, and in the products, we have 2 moles of gas. So we're decreasing the amount of gas particles flying around, which would decrease the number of microstates, which decreases the entropy. So the sign, at least, for the entropy of the system would be negative. So you have a negative delta S of the system. So in this case, it doesn't really matter what the sign or what the magnitude of that is, because the delta S of the universe is equal to the delta S of the system plus the delta S of the surroundings. And if both of those numbers are negative, and so we determined that this was a negative, and we can quantify this one, negative 5.47 times 10 to the 2. Bless you. It doesn't matter how big or small that entropy change in our system is, right? A negative number plus a negative number is going to be another negative number. So is this reaction spontaneous? If it decreases the entropy of the universe? Not spontaneous. I saw some people mouthing no to me. It's okay, you can say it. So it's non-spontaneous. So cool. We've put together a way now to calculate, really specifically, the entropy of the surroundings and how that changes. But we're still just using, right, the sign of the system. And that'll be coming up shortly. So one last question here. So do biological systems contradict the second law of thermodynamics? Right, so by taking energy from their surroundings, any biological system, they're synthesizing large and complex biological molecules. Right? Plants and animals tend to concentrate energy, not disperse it. So how can that be so? How is it that we're able to create larger and larger molecules that are more and more energy dense? Do you remember heat tax? So really, every step of creating these larger and larger molecules requires a source of energy from something else. So right, we eat plants. The plants are producing plants and animals, unless you're a vegetarian or vegan. And then those plants are getting all of their energy from the sun. So ultimately, we'd have to look at the entropy of the sun and how that's changing. And if you think about that, we have the sun, excellently drawn, in, well, do you know how cold space is? It's like 2 Kelvin. So if the amount of heat that the sun is producing is being dispersed into almost absolute zero, right, that's generating a lot of entropy, or increasing the entropy of the universe by a lot. And so it's by the sun increasing entropy of the universe that we're able to sort of feed off of that and some of that energy, and not break the second law of thermodynamics. So ultimately, the sun increases entropy enough that we can exist without breaking the second law. And then, of course, on a smaller scale, every one of these processes is not efficient and is releasing energy, and is also increasing entropy further. Alrighty. So now we're finally getting to how do we calculate for any given reaction, or how do we predict whether or not it's going to be spontaneous or non-spontaneous? So we can take now our second law of thermodynamics. Well, what sort of comes out of the second law of thermodynamics, that change in entropy of our system plus the change of entropy in the surroundings is the entropy of the universe, changes the entropy of the universe. And our equation here where the change in entropy of the surroundings is related to how much heat is released or absorbed, the enthalpy, of our reaction. So we plug this in, we'll get delta S of the universe equals delta S of the system plus negative delta H of the system divided by T. And then if we take this one step further, we can get an equation that'll give us, as the title hints, an equation for Gibbs free energy. So multiplying both sides by negative T, we'll get negative T delta S of the universe equals negative T times the delta S of the system, and then plus delta H of the system, because that negative T there will cancel out and also cancel the negative. This equation is just one small step away from Gibbs free energy. So same equation here, slightly rearranged. So negative T times the change in entropy of the universe, delta S, is equal to delta H minus T delta S. And this negative T times the change in entropy of the universe is G, or Gibbs free energy. So the change in Gibbs free energy is delta G equals delta H minus T delta S. And now we can drop that system subscript because all of these quantities are talking about or describing our system. Also good to remember is G is equal to negative T delta S of the universe. It's helpful to remember this because we're going to start talking about how we can use Gibbs free energy. So this relationship between G and the entropy of the universe is the basis for whether or not a reaction is spontaneous or non-spontaneous. But the relationship is sort of flipped. Right? If we have a negative value for G, then negative Gibbs free energy divided by negative T equals a positive change in the entropy of the universe. But if Gibbs free energy is positive, then it's positive G divided by negative T would give us a negative change in the entropy of the universe. All right. So the change in Gibbs free energy for a process, and we're going to be talking about chemical reactions, a process occurring at constant temperature and pressure is proportional to the negative of delta S of the universe. Right? So that's that inverse that I was talking about. And so we can use delta G as a criterion for whether or not something is spontaneous or not. And just like we talked about, right, chemical potential determining on whether something was going to spontaneously fall or not, then talked about sort of briefly, well, what if we had some quantity, some way to quantify chemical potential and change in chemical potential? And so that's what Gibbs free energy is. It's analogous to that chemical or mechanical potential energy. So chemical systems want to lower their potential energy, just like when you drop something, the potential energy of the object that you drop decreases. So just another way to remember that when delta G is negative, when our change in energy is negative, we have a spontaneous or process that's going to be spontaneous. So delta G can be calculated solely now with reference to our system. We can use, which you should have gotten in Chapter 6, and even a little bit in Chem 20, right? Enthalpies of reactions, standard enthalpies. So if you have a chemical reaction, there are standard enthalpies, and you can calculate also, right, by combining standard enthalpies to get overall enthalpies of reactions and get delta H. And then we can also get delta S, as we calculated, we calculated delta S just based on the change in energy, and we're going to get something better than that for delta S. Sorry, I don't remember seeing this graph in the book. We're just going to press on. So when we have this equation now, and what we're concerned with is ultimately the positive or negative sign of delta G. So there are some cases then where, depending on whether or not delta H is negative or delta S is negative or positive, we can have reactions or have conditions that are always spontaneous, conditions that are never spontaneous, and some that depend on the temperature. So our first case here, where we have a delta H is negative and delta S is positive. So we have, with delta H being negative, that's an exothermic reaction with a positive change in entropy. So that reaction is going to be spontaneous at all temperatures. Because if we plug in delta G equals negative, just plugging in the standard enthalpy of the reaction, 163.2 kilojoules minus some temperature times, and we're told here that it's a positive change in enthalpy, which we could also get from the balanced chemical equation, right? Because we're going from 2 moles of gas to 3 moles of gas. So it's going to be a positive change in enthalpy, increasing the enthalpy. So this has a negative sign, and we're subtracting something else that's going to have a negative sign. So there's no temperature at which, because we have temperature is absolute, there's no such thing as negative temperature. There's no temperature at which the sign's going to flip. And so it's always going to have a negative delta G. So if delta H is negative, delta S is positive, always spontaneous. For case number 2, now we have delta H is positive, delta S is negative. So we've flipped both of the signs. So now we have an endothermic reaction and a negative change in entropy. And again, we've got gases reacting. This must be a nuclear reaction, because it's 3 moles of oxygen gas to create 2 moles of nitrogen, well, trinitride. But our delta H is positive. So if we plug in, again, just the general signs here. So positive delta H, 285.4, minus some T, right? And temperature is always positive. And then it's a negative change in entropy. Now that negative change in entropy, we're subtracting a negative number, which means we're adding a number. This is always going to be non-spontaneous, because delta G is always going to be positive, doesn't matter what the temperature is. Now the more interesting cases are where we have the same sign for delta H and for delta S. So if delta H is negative and delta S is negative, like for water freezing, So we have the standard enthalpy, which would be the delta H of fusion. So our delta G is going to be equal to negative 6.01 kilojoules minus T, and now times negative. Because we're decreasing the entropy by constraining the water. So that makes this positive, right? And so now, depending on what this S value is, right, we can plug in a number for S and then multiply it by a temperature, and at some point, this will change from being negative to being positive. So here now, depending on the temperature, we could have a spontaneous process at, think about this, spontaneous process at low temperatures, and a non-spontaneous process at high temperatures. And we could actually figure out what delta S is here because it's water freezing, so we know the temperature at which that's going to switch. And so you could plug in 273.15 Kelvin and calculate what delta S is. Or what delta S would have to be what delta S would have to be for delta H or delta G to be 0. Right? Because exactly at that flipping point is where you switch from being spontaneous to non-spontaneous. Then the last case that we haven't covered is going to be positive for both enthalpy and entropy. So for an endothermic reaction with a positive change in entropy, so now we've got a liquid, water boiling, forming a gas, at least at 100 degrees C. This is going to be delta G equals positive 40.7 minus T times a positive change in entropy. So this flips when we have a spontaneous process. That makes sense in the context especially of water boiling, right? Water will boil spontaneously as long as the temperature is high enough. So at really high temperatures now, it'll be spontaneous, but at really low temperatures, it'll be non-spontaneous. And that change will happen at 100 degrees Celsius. So even though we have this equation for Gibbs free energy, we have standard enthalpies. We can find the temperature, be given a temperature easily enough. We still don't have a way to sort of standardize entropy. Oh, right, this is the table first. So when delta H and delta S have the same sign, spontaneity depends on the temperature. In the cases where they have opposite signs, they'll be either spontaneous or non-spontaneous. And if you're ever, you don't have to just memorize this. You can always write down, well, the thing you would have to memorize is delta G equals delta H minus T delta S. Plug in a positive sign for both of those and see if there's any number for temperature that would make it spontaneous or non-spontaneous, right? If the sign flips. Always better to have a way to figure it out than to just rote memorize these things. Oh, see, that must have been a typo. I was like, it's really weird that they threw in this nuclear reaction. Okay. So consider this following reaction, and now we're given a delta S. And we will get to, I promise, how to calculate that. You can see at the very bottom, it's on the next slide. So if we want to calculate delta G at 25 degrees C and determine whether the reaction is spontaneous or not, all we have to do is remember the equation. Delta G equals delta H minus T delta S. And for now, we've been given these values. The one key thing to remember here is that the units of energy are different. So one has to be in kilojoules, the other has to be in but the other is in joules. So we need them to both be in the same. Whichever one you pick, it's kind of dealer's choice. Because ultimately here we're looking for the sign, or if the question asks for a specific unit. So 137.5 kilojoules minus the temperature in Kelvin. So 273.15 plus 25. So 298.15 Kelvin times a negative 120.5. Oops. And then, I'm sorry, literally just said this. So make this in kilojoules. So negative 137.5 minus 298.15 times a negative 0.1205. So delta G is a negative 101.6, bless you, kilojoules. So is it spontaneous or non-spontaneous? Spontaneous, right? Our chemical potential energy has decreased. So if we decrease our chemical potential energy, that's spontaneous. And what effect would increasing the temperature have? Would it make it more spontaneous? Or less spontaneous? Which is not really a thing. If we increase the temperature enough, will it become non-spontaneous is really the question. It's either spontaneous or not. Yeah, so you could go back to the chart and say, look at it and see, based on the signs of delta H, delta S, whether or not it's going to be spontaneous at low temperatures, spontaneous at high temperatures. You could also just pick a number and plug it in for the temperature, right? We can just plug in a higher temperature and see if it gets closer to 0 or not. So might as well just try it out. This is one of those prove it to yourself kind of things. Right? Like check to see if this works. Try and figure out the flipping point. Like at what temperature does this become non-spontaneous? So let's just put in, I don't know, pick a large number. Number larger than 298. 500. I was thinking 500 too. So we'll put in 500, negative 0.1205. That doesn't change. That's kilojoules per Kelvin. Oh, well, it wasn't enough to make it non-spontaneous, but it does tell us something. So now it's negative 77.25, and it did get closer to 0. So we kind of extrapolate out and say, if we keep going, it will eventually get to 0 and then become positive. Although it would probably need to be, well, about 1,000 Kelvin. All right, so what is this delta S number? Where did that come from? So with standard enthalpies, if you remember Chem 1, for standard enthalpies, those are all based on standard states. So depending on whether it's a solid, liquid, or gas, those are a certain set of conditions that we've sort of, not necessarily chosen arbitrarily, but there's conditions that are convenient, right? 1 atmosphere for gases, 1 atmosphere and 25 degrees C for solids or liquids. And then if something's in a solution, it's a concentration of 1 molar. And these are things that are generally easy to achieve in a lab. That's actually why standard temperature is 25 degrees C. Well, standard temperature is in terms of standard temperature and pressure, but a standard temperature that's often used is 25 degrees C because it's slightly warmer than room temperature. And it's a lot easier to warm things up than it is to cool them down. So for enthalpy, we had to do this because there's no absolute enthalpy that we can calculate for anything. Just standard ways that we can get relative enthalpies. For entropy, that's not actually the case. We can calculate a standard entropy, and it's an absolute molar entropy. Just like next slide. So for these standard entropies for a reaction, we'll use these standard entropies for the products and the standard entropies for the reactants to calculate the overall change in entropy for a reaction. But these standard molar entropies are defined based on the third law of thermodynamics. So, and this is still an ongoing project to try and get things to absolute zero. We've gotten really, really close. Involves lasers, lots and lots of cooling in series. But we can calculate absolute entropy because the entropy of a perfect crystal at absolute zero is 0. And that's because this crystal at absolute 0 isn't moving. So the temperature, the way that we measure temperature in general is the average kinetic energy of the particles in a substance. So like the temperature of the air in the room is roughly the average of the kinetic energy of those particles flying around. So if you extrapolate that all the way down to 0 motion, 0 kinetic energy, then we get this perfect crystal that's not moving. It would be the only thing in the universe not moving, because even outer space is 2 Kelvin. And so if we plug in then, if this isn't moving, these atoms are locked in place, then we have a single, one possible way to arrange the components. And so when we use Boltzmann's definition of entropy, the natural log of that one state is 0, times the Boltzmann constant gives us an entropy of 0. So the molar entropies that we use to calculate entropy of reaction are based on that absolute 0. Okay. So we've got all these tables of molar entropies. You don't have to calculate molar entropies or do a PhD to figure out how to do that, because I've not looked into it, but I'm sure it's an extensive process. It just got to be brutal to do it for anything. So you have tables, though, right? You can look up these values, and they'll be provided to you on exams, at least a table of values that you can look them up. And you'll notice here for some things, right? For water, we have the standard molar entropy of water as a gas, and we have a different entropy for water as a liquid, and a different entropy for water. Oh, it's not on this list. It would be a different molar entropy for water as a solid. And so there are a lot of things that affect molar entropy, right? If we have difference between a gas, a liquid, and a solid, those are going to have different amounts of entropy because there are different numbers of ways to arrange the components. So for any of these at 25 degrees C, we calculate the standard entropy of any substance is the energy dispersed into 1 mole of that substance. And this is because entropy is an extensive property. If we had more water, that's more molecules, so more ways that we could arrange all of those molecules. So, and it's an extensive property that depends on how much of the substance that you have. And it's affected by a lot of things then. So the state of the substance, like I already pointed out on that last chart, solid, liquid, or gas, the molar mass of the substance, the particular allotrope, which, if you don't remember, is the specific arrangement of a solid. So something like sulfur, pure sulfur, can have a lot of different allotropes. They even have different colors. But but each of those different configurations of the atoms will have different amounts of entropy. And then we also have molecular complexity. So if you get a more complex molecule, changes the entropy. Then also the extent of dissolution. So how dissolved or dispersed in a solution is it? So I'm just going to quickly go through some of these somewhat generally and talk about the trends. But in general, we're still using the same definition of how many ways can we arrange the components. So for solids, liquids, and gases, the solid is going to have less entropy than the liquid, which is going to have less entropy than the gas, just because as we remove constraints on the components, there's more ways to arrange them. And so we get big jumps in entropy just by going from a liquid to a gas. Right? Pretty much, well, more than doubles the entropy, standard molar entropy. Molar mass also has an effect. So if we look at just the noble gases, all in the gas state, that entropy increases as they get larger. So it's out of the scope, outside the scope of what we're going to talk about, but essentially, as they get larger, there's more ways for them to, or they have different energy levels which are more closely spaced, so there's more gradation within those energy levels, and you get more options that way. Right? So even though it's outside the scope, it still has to do with how many ways can we arrange the thing. Allotropes are interesting. So like I said, some things have two or more. Sulfur happens to have a lot of different allotropes. Even ice has different allotropes. So these entropies are different because of the way that the molecules are arranged. So like diamond, which is very hard, very, very different from graphite. In a diamond, the motions of the individual carbon atoms are highly constrained. It's a tetrahedral repeating pattern. And so every molecule is sort of held in from all sides to try and be in roughly the same spot. Whereas in graphite, or graphene, or like any other form of carbon, is generally in sheets. And so while they're constrained by sort of the ring of carbons around them, they have more freedom to move up and down and in other directions. So there's more vibrational modes. So more ways to arrange energy. Oh, I want to point out too that it is, in this sense, doubling that amount of entropy, but it's still sort of in absolute scales, it's a small change in entropy. Molecular complexity. So for any given state of matter, entropy will increase with the complexity because there are more places to put energy. So if we have something like nitrogen monoxide, it can translate, so it can move side to side, or it can rotate or spin. And then there's also vibrational motion, where it's the bonds stretching, right? And so if you add another bond on there, now that can stretch in a different direction, and it can also vibrate back and forth. And so as you add more and more things, there are more unique ways that it can vibrate. And those are a pretty large increase in entropy just by increasing complexity. So something like carbon monoxide and what is that? Ethylene. Wow, ethylene. Have similar molar masses, but ethylene's more complex, so it has a higher molar entropy because it's 4 molecules bound together instead of just 2. And then, of course, as you increase complexity, you're generally adding more atoms, and so the molar mass also increases. So if we go from nitrogen to nitrogen dioxide, we get an increase in molar mass, and then an additional increase because of the complexity. So if we also dissolve something, dissolving a crystalline solid into a solution will increase the entropy, because now it's gone from a solid to not necessarily a liquid, but essentially the same freedom of a liquid. So becoming dispersed throughout a solution increases that entropy. Okay. Now we're finally getting to some calculations. I'm sorry, this has all been very just like expositional. I've just been sort of saying lots of things, and happy to have you guys nodding along. It's the nature of the beast. So now we can use these entropies. We've talked about all these general trends in sort of like the complexity of things. So I could ask you like, oh, would this molecule have more entropy than that molecule? And then you could look at them and say, well, does it increase the size? Does it change the state? All of these different things. And probably won't layer many of those on top of each other because, right, blurs things. But in terms of reactions, which we've been sort of has been the goal of these first 60 slides, we now have molar entropy. We had molar enthalpy. We can get temperature, and so we can calculate Gibbs free energy. And so for any reaction, we just look up all of our reactants and our products and their molar entropies. And remember, the amount of them, or molar entropy is an extensive property. So we can multiply those by their coefficients. And then it's our products minus reactants. As with so many things, right? It's either products minus reactants or products divided by reactants. And this is the fancy math notation for the sum of the number of the product times the molar entropy of the product minus the sum of all of the molar entropies of the reactants times the number of reactants, or the coefficient. And then, unlike standard enthalpies, which sometimes are 0, standard entropies are always non-zero, unless it's 0 degrees Kelvin, or 0, not degrees Kelvin, 0 Kelvin. All right, so let's calculate a thing. So calculate delta S, the reaction for the balanced equation. So for this balanced equation, we have very conveniently all of the molar entropies that we need. So you say the delta S, this reaction, is going to be equal to 2 times whatever the molar entropy of hydrogen sulfide is, plus we'll do large parentheses here, plus 3 times whatever the molar entropy of oxygen is, minus 2 times H2O, plus 2 times SO2. So we'll just plug in those molar entropies. So 2 times hydrogen sulfide is 205.8. So then 3 times the molar entropy of oxygen, so 3 times 205.2 minus the 2 times molar entropy of H2O, which is 188.8, plus 2 times the molar entropy of sulfur dioxide. I mean, you solved my puzzle. Congratulations. Move these over here. Nope, I did that wrong. There we go. Perks of using an iPad. Thank you. So, yeah, when you type this into your calculator too, the only thing you have to make sure you do is put parentheses around this back half. The calculator will do the correct order of operations for these. Or you can do them separately and then subtract. Plus 2 times 248.2 lost a decimal. So delta S for this reaction four sig figs. And then the units are joules per mole Kelvin. Did you get the same thing that I got? Now just looking at this reaction, does the sign of delta S make sense? Can somebody tell me why? Yeah, because we got gases and we're decreasing the number of moles of gas. So you have 5 over here and 4 over here. So that's a quick way to check that you didn't make the same mistake that I did and put them in the wrong order, right? Because the number will be the same, but the sign will be backwards. Always good to have quick checks. So you would think for all of the talking about this that we might have had a more complicated or complex problem to solve here, but it actually ends up being conveniently simple. But hopefully not too simple that you forget how to do it. That's the other trap. Okay, so we can calculate molar enthalpies or molar entropies for the reaction based on these standard entropies. So now we can calculate the standard change in Gibbs free energy and determine if reactions are going to be spontaneous or not. So 3 methods here. We can go and calculate delta H of the reaction and delta S from the standard enthalpies and the standard entropies, and then use our Gibbs free energy equation. Or you might have just Gibbs free energy values for reactions. And then based on how you add those reactions together to get an overall reaction, you got to add, subtract, multiply, or divide to get to the, I guess you'd never divide, but multiply to calculate an overall Gibbs free energy for the reaction that you're interested in. Or you can calculate from the free energy changes for the steps in a stepwise reaction, which I guess is what I was talking about.